Okay, so assalamu alaikum and good morning. Today we'll continue talking about synchronization and our focus is semaphores, okay? We had a simple intro to semaphores in our previous class. Today we're gonna repeat that. We see basically a concept of a semaphore implements available resources in the system. Implements available resources in the system. In fact, a semaphore, in terms of implementation, is an integer value. Is an integer value with two operations, and these operations are atomic operations. One operation that will increase the value, the other will decrease it. Okay, the increase and decrease is by units of one at a time. However, later on you'll see that we have other implementations of semaphore that you can increase this value with more than one, okay? And the same thing, decrease it with a value that is more than one. So it's an integer value, and we have the operations P and V. The origin is Dutch, okay, and the words are there. You could read it better than me. However, the meaning of P is to test, okay, and V is to increment. V is to increment. The value, if it's a resource of the system, then this resource will be acquired by processes, because as we know, processes, they do what? Acquire resources. They need resources for them to execute, correct? So a process, when needs the resource, will call the method acquire. We'll call the method acquire. And by acquiring a resource, it means that the system will be allocating a resource to the process. Means the number of resources with the system will be less one. That's why acquire decrements the value of the semaphore. Decrements the value of the semaphore because it gives away one instance of the resource to the process who is requesting for it. And release, it does the opposite thing. Once the process you finished using that resource, then it will do what? It will signal that, and the system will deallocate that resource. Means the system is claiming it back, and by that the value of the semaphore is incremented. So we see the release method. Release is called once the process is finished with the resource. And this means the system will have more resources, right? So decrement by acquire and release by value. What you see here is not an actual code. It's basically pseudocode, right? It's a pseudocode in which when a process asks for a resource, the system might allocate that resource and might not, okay? If the resource is available, it's allocated. However, if it's not available, then that process should wait for it until it's available, So how are we gonna implement that kind of wait, which is here, right? How are we gonna implement it, which means block the process if it is asking for a resource that is not available, right? This blocking, we can do it in one of two ways. Basically, we can have the process keep checking the condition of that resource when it's available, right? And we said that is a busy wait. So you're gonna have a loop in which there is a condition checking the availability of the resource, and the body of the loop is empty. Do you remember that busy wait? We used it with the producer-consumer problem, okay? And in this case, what happens is that the process is wasting CPU cycles, because it's not doing anything useful except checking that condition for a change, right? For a change. However, this change can only happen when the release method is called. Right? Because releasing, that will increment the number of resources, right? So the system will have resources. And who could call the release? Another thread. So keeping the CPU busy checking a condition that could only change by another thread running is not doing anything useful, right? In fact, it's delaying other threads from calling, most likely, release, okay? So this implementation has this kind of disadvantage. Another implementation might be on a process acquiring a resource. If the resource is not available, then that process should suspend itself. Suspend itself. And I think we have seen how you could do that in code. For example, in Java, the process can call what? Wait. Can call wait. So in this case, the body of the condition checking for the resource is not empty. The body has wait. Has what? Wait. Okay? And by that, the process will be giving opportunity to other processes to execute, and hopefully one of them is going to execute what? The release, in which the system will claim back resources. So that's the good thing about the second implementation, not being busy wait, suspension. Okay? However, the busy wait implementation is also useful in a case. Suspension, by the way, suspension involves what? Context switching, right? A process will be suspended, so we're going to have a context switch, and then another process will take over, right? So that context switch, we call it what? A delay, an overhead, right? And the time of it is very critical. What we want is to reduce the number of context switching when possible. So if we have multiple processors, okay, we have multiple execution environments for the different threads, it's better to use what? Busy wait. Because the processor who's acquiring a resource that is not available on one processor can keep checking the condition, hoping that other threads who are running on other processors might release. And in this case, we are not doing any context switch. And the process is acquiring can just continue in a very short period of time if a process released a resource while running on other processors. Do you understand? Okay. Now these semaphores, I said they do implement resources in the system. So the value in the semaphore, which is an integer, if we restrict it to 0 and 1, okay, taking only these two values, by that we are implementing a resource that has two states, 0, 1, okay? So we're going to model this to have the concept of the lock. The semaphore, when it's 1, a resource that has one instance, okay? It's 1 means I have one copy of it. And it is available. It is what? Available. 0 means it had been given to some process. And it means not available. So this is equivalent to the locking mechanism in which the acquire method decrements the semaphore, right? Decrements it. So if it's 1 and we acquire it, 1 means available. We acquire it, acquire will decrement it, will make it 0, make it what? Not available. So this is what? Lock. The lock method of the concept of a lock, right? Or the acquire method of a concept of a lock, obtaining the lock, right? And the release, the value is 0, and the process released it. That will set it to what? To 1, because release increments. So it was not available. The process finished using the critical section, calling release, means it is setting the lock to be available, because release will change the value to what? 1. Okay, so that's the concept of semaphore with two states, 1 and 0. Initially, it's 1, means it's available. Okay? We call this a binary semaphore, and it's a direct implementation to a mutex, okay, which is a locking mechanism. So from now on, if we want to implement a lock for the critical section, basically we just need to create a semaphore, initializing it to 1, And before entering critical section, we call the semaphore acquire method. After leaving critical section, we call the semaphore release method. As easy as that. Okay? On the other hand, system might have number of instances of the same resource. Number of instances of the same resource. For example, hard disk. You might have like 2, 3 hard disks attached to the system. Ports. You might have more than one parallel port, more than one serial port, USB port, and so on. So when we model these resources, okay, we model each one of them using a semaphore. Okay, a semaphore with a value that had been set to the number of instances of the resource. For example, if I want to implement the, say, the USB port, and I have 3 USB ports in my system, then I can model that with a semaphore of 3. Initially, I have 3 instances of this resource. Now, processes, they can acquire. They can ask for this resource. The system can easily give away 3, because 3 are available. So, can serve 3 processes where each one of them acquiring 1 copy of this resource. However, the next what? Requests to have that resource won't be served. They have to wait because all the 3 had been allocated. So each time we allocate an instance of a resource to a process, what do? We decrement the value. We have list resources. So if it was a 3 and we allocate 1, then the system will have what? 2 as a result of acquire, because acquire decrements. And then acquired another time, then acquire will decrement again, so we have only 1. Acquire another time, then we have what? 0. Acquire another time, the value also will be decremented. It becomes -1. -1, but the process will wait. Will what? Will wait. So whenever we decrement the value, we check. Okay, we check. If it's negative, means the process is not given the resource. It's waiting for it. It's waiting for it. Okay? So acquire does this. Okay, the body of acquire. Decrement value. And then check value. If it's negative, means there were no resources. So for that, the process must what? Wait. So the implementation like that. Decrement value and then check value. If it's negative, call wait. Okay? Call wait. So if value is getting negative values, then what does it mean, the negative value? Say the value is -5. What does that mean? Excellent. 5 processes are requesting this resource, which is not available. So we have 5 waiting processes for this resource. And if value equals 3, means the system has 3 instances of that particular resource. We can use this concept to implement solutions to various problems. And we're going to show you how. So basically, we're going to block a process that is acquiring a resource and setting the value to be negative. Okay? But if we block a process, then we have to unblock it with another logic. And that logic would be release, right? Because we only have acquire and release. So when we release, what should we do? Call, in Java, for example, we call what? Notify. Yeah? We call notify. Whenever a process releases a resource, notify is called. Notify is called. A problem that arises with using semaphores. We said what we're doing here so far is to implement mutual exclusion, to make sure that there is only one process is in its critical section at any given time, one or none. okay, but not more than one in the critical section. That's mutual exclusion. However, there is something else that might happen which we need to handle it, and that is called deadlock. Called what? Deadlock. Consider this situation. If we have two processes assumption, excuse me, these processes P0 and P1, and assume that we have two resources in the system, each one of them is a single instance, a single instance. These resources are S and Q because we model each one of them with a semaphore. The first resource, we modeled it with semaphore S. The second resource, we modeled it with a semaphore Q. Now assume the logic of execution for these processes is acquiring these resources. So P0 acquiring the resource S means it calls acquire with the semaphore S. After that, we had a context switch. Okay, let's follow this scenario. After P0 acquiring resource S, we have a context switch. Now P1 is running, and P1, the logic of it says, acquire resource Q. So resource Q is available, and it had been obtained, right, allocated to process 1. And then the logic of P1 says, acquire resource S, because P1 needs these two resources together to continue its work. Okay? However, resource S is currently being used by P0. Okay? Then we're going to have a context switch because the acquire method will set process 1 to wait, acquiring a resource that's not available, right? Now P0 will continue and calling acquire the resource Q. However, the resource Q is currently being used by P1. Okay, and P1 will not release it. So we're going to have a context switch, and so. So each one is holding a resource that's needed by the other and asking for the resource that is held by the other process. None of them will proceed. The result is deadlock. Okay, we're going to look at this in the next chapter and the different ways of handling deadlock, including prevention, detection, and avoidance as well. Some resources, as you know, in the system, they are very expensive resources, or they are common to processes, and for that we're going to have some, or we should expect some kind of starvation, okay, because they're going to have many requests from the processes asking for them. Now let's use the concept of semaphores in solving some of the common problems in synchronization. We start by the most generic problem, which is basically the critical section problem. Critical section problem is very generic in a way that the worker will be executing a code that's critical, another code that's not critical, non-critical code, and going to do that continuously in an infinite loop. Okay? What we want to do is to guard the execution of the critical section. Guard the execution of the critical section. So if this is the code of the worker, and you know we have multiple workers, these are threads, okay? Now, then we need to coordinate how they work, okay? The coordination is done by guarding what? The critical section. So we have to have a code before critical section, another one after the critical section. Obtaining the lock and releasing the lock. So we can do what then? We can use a semaphore, okay? So in our main application, we create a semaphore with the value 1, a binary semaphore. And whenever we create a worker thread, we send that semaphore to it. So all the workers, they share one semaphore, which is a binary semaphore that implements the locking mechanism for the critical section. Correct? So now, simply before the critical section code here, okay, we can call what? Sem.acquire. And after, we call sem.release. That's all. So what we can see here, comparing this solution to previous solutions, in terms of easiness, isn't it very easy here, the code, right? You already have a locking mechanism. Just you need to acquire and release. Obtain lock, release lock. That's all. knowing that you have the concept of the semaphore available for you. For the time being, we're going to use a class to implement this, and this class is basically like this. Class has value, it's called semaphore. So you can create a semaphore with any number of values there. And it has acquire and what? Release. The acquire, it does decrement the value and check it. So here I'm checking if the value is less than or equal to 0. If I don't have what? Resources. Then what should I do? I should set this process to wait. I should set it to wait, and I could what? Decrement value as well. If you're going to have the decrement value here or before the while, both of them will do. Okay? On the other hand, the release method, you can see it increments because the system is claiming back the resource. You're going to have more resources. And it calls what? Notify. As simple as this, the semaphore. So do you know how to code this semaphore? Yeah? A class, it has an integer value, receives the initialization for it. It has two methods, acquire, release. Acquire, it checks the condition to block or basically just leave the, let the method return, okay? So if the value is less than or equal to 0, means we don't have resources. In that case, we're gonna have the process to wait, okay? And the release simply increments and calls notify, okay? Now to get back to the other problems. So in the critical section problem, your main class basically is going to do this. Create a number of workers and send the binary semaphore to each one of them. They all share the same semaphore, all share the same lock. So in this case, we have 5 bees workers. Okay, here we're gonna be creating them. Each one, we will give the initialization that is needed for it. And one of it is what? The semaphore. And semaphore is what? A binary semaphore that we have created before. And here we start all these workers. Next, we look at another problem, which everyone is familiar with now. It's the producer-consumer problem. We have seen different solutions for it before using yield, wait, notify all pairs. So now, if you're gonna implement the solution for the producer-consumer problem, then the most important thing when you use semaphores is to find the appropriate model for the solution, okay? So what we have a shared area, and that is the bounded buffer. Basically, this bounded buffer, we want it to be accessed by one thread at a time, correct? So we don't want multiple producers or multiple consumers or a combination of both to access bounded buffer at the same time. That won't work, right? So what we want is to guard the execution or the access to the bounded buffer, which means we're going to have some kind of looking mechanism to access the bounded buffer. So would that be a binary or counting semaphore? Binary semaphore is just a look, right? If you have it, then you can access this bounded buffer. If you don't have it, you can't, right? So that's the very first model or the very first semaphore in the solution. Now, let's look at the cooperative processes, who are the threads here of type producer and consumer, right? The producer to produce needs resources. Consumer to consume needs resources. Who can tell me what are the resources needed for a producer? Producer was restricted to insert an item in the bounded buffer if there were no empty locations, right? So we can think of the empty locations being what? The resources for the producer, correct? Empty resources, empty locations are the resources for the producer. So initially, what do we have? The bounded buffer empty. right? So if it has a size of 5, then initially I have 5 resources for the producer. And the producer will be doing what? Using these resources, acquiring them and releasing them. Correct? If they were not available, then the producer would wait. So here I'm talking about what concept? Counting or binary semaphore? Counting semaphore. That is initialized to the number of empty locations in the array. And initially, this is the size of the bounded buffer. The size of the bounded buffer. This resource is used by whom? Producer. Now let's look at the consumer. What are the resources of the consumer? Are the items who are in the bounded buffer. These are the filled locations. Filled locations. So initially we have how many of them? 0, none of them. So I can say we model the resources of the consumer using bounded or binary semaphore, counting or binary semaphore? Counting semaphore, okay, counting semaphore. Initially is 0, but it might increase later on when the producer or producers start to produce, correct? So that's the concept. So initially what I have here, I have 3 semaphores. One is the mutex, which will implement the locking mechanism for the bounded buffer, and then full, that implements the, empty, that implements the empty locations for the producer. These are resources for producer, and the full, which is basically the resources for the consumer. Now, at the very beginning, I initialize, we still need to use in and out, and these are zeros, okay? The buffer we created, okay? And we initialize these semaphores. Initially, the lock is available, right? For the bounded buffer, is unlocked. And then we have a number of resources for the producer equals to what? Equals to the buffer of the buffer size, okay? Number of resources for the producer equals to the buffer size. So I have a semaphore and initially initialized to that. And I have 0, okay? No resource for the producer, for the consumer, for the consumer. Now we can model or we can code insert and remove accordingly, okay? For a producer or a consumer to insert, they have to use these semaphores now. The logic of these semaphores plus the code to do the removal or insertion of an item, which is the code that we have seen before. Let's look at insert first. For a producer to insert an item, then it should obtain the lock to the bounded buffer, right? And then it should acquire a resource. Immediately after the acquire means after the acquire returned, and when the acquire will return, when that resource is really allocated. Otherwise, it will be blocked, right? So immediately after acquire, what we would have? We would have the code for insertion. And we're done, right? Okay. So obtain the lock of the bounded buffer and then acquire the resources needed by the producer. However, if from the very beginning the producer doesn't have resources, why should it obtain the lock on the bounded buffer? Right? So first, the logic says, so this is later on how you rearrange the logic for an optimal solution. Okay? We say that first, check if the producer can or has some resources to produce, and then obtain the lock on the buffer to perform the actual insertion. To perform the actual insertion. So that's the code. We have empty.acquire. Empty models what? The resources for the producer. And initially, all of them are empty. And if it returns, means we have resources for the producer. Then we can have hold on the bounded buffer, perform the actual insertion. And then release what? Release the lock, which is for the bounded buffer, okay? And then release the lock for what? For what? What does the release do? What does the release do? Decrement or increment? Increment. Okay, by inserting an item, by the producer inserting an item, what does that mean? The number of resources for the producer decremented, correct? And the number of resources for the consumer incremented, okay? So that's why we call what? Full dot release, where full models the number of resources for what? The resources for what? The consumer, okay? The consumer. Do you understand that? Okay. Because here we have like direct effect of one resource on the other, because they are what? The complement of each other. On the other hand, similarly for the remove, we have full dot remove, okay, and we have mutex dot acquire, okay. So first we check whether there are items for the consumer to consume, and then we get hold on the bounded buffer, then the actual removal, okay. And then after that, releasing the lock on the bounded buffer by saying mutex release, and then releasing the lock or what? Releasing a resource. Releasing a resource. By consuming means the system will claim back a resource. However, this resource now empty means it's a resource for the producer, okay? And what implements or what models the producer resources is the empty semaphore. Now, if we exchange these two, the order, we have mutex.acquire followed by empty.acquire. What might that result in? The lock of the bounded buffer is obtained first by the producer, okay? So it's with whom? With the producer. Assuming after that the producer called empty.acquire and the buffer was full. What happens? It will wait, right? Wait. However, it is waiting, still holding the lock, which is what? The acquire lock, right? The mutex lock, right? Which is the lock to the bounded buffer. And when the consumer tries to execute, it cannot get hold on the lock of the bounded buffer. So we have what? Deadlock. Right. You study the code later on, you get to know more about it. And here is the application to execute them. I think we have seen something similar to this before. I mean, this is the code of the producer, okay? And similarly, the code of the consumer, which this is how we execute them. Next is the readers, writers. Readers, writers. Readers, writers problem, we have a data set and it's shared by number of readers and writers. As you know before, right? We have explained this problem before. Now, what we need here is a locking mechanism to what? To the database, okay? To the database itself. We need the thread to get hold on the database before it starts reading or writing, correct? We also need to have some kind of looking mechanism on one shared variable, if you remember, which is readers count. Readers count, because readers count is accessed by multiple readers. For these, we use two semaphores, and these semaphores are counting or binary? Binary semaphores. Binary semaphores. And then we implement the logic of the locking mechanism. The logic of the locking mechanism. Basically, me show you the code here is better. What we need is to implement 4 methods, and these methods, so after initializing these semaphores, mutex and db, where mutex for the readers count, because shared among readers. We don't want multiple readers to update this variable, okay? We want to coordinate how is it updated simultaneously by these readers. And the db is the lock for the database. db is the lock for the database. Okay. Initially, we have no readers, okay, and we have these available, the locks for the readers count and for the database itself. Now, acquiring the read lock. Acquiring the read lock. For a reader to start reading, it must get hold on the database, right? It must get hold on the database. And then it should get hold on the readers count, correct? Now, which one we should do first? This is similar to the logic that we did just now with what? With the producer-consumer problem. So first, the readers should have hold on the lock of the readers count, which is what? The mutex. So the mutex implements the lock for the readers count, right? And then update the readers count by incrementing it, right? And then get hold on the database. Okay. If there are already active readers, then the new reader who's joining should also get hold on the database, or no need? No need, because it's already held by readers, right? So who should get hold on the database? The first reader, right? The first reader. That's why we say if reader count equals 1, after we incremented the reader's count, means you are the first reader. And if you are the first reader, try to get hold on the database. And this will return only if there are no writers. In fact, no writer, because only one writer. Okay, so db.acquire. Okay? db.acquire. And then after that, release the lock on the reader's count so that other readers can also join later on, right? Now, the release does what? Decrement the number of reader count. Okay, decrement the number of reader count. But reader count is guarded by the mutex. Okay, the mutex, this is the lock for the reader count. So gain it first, then decrement reader count. The database is still held by readers, right? The last reader will release the database. So that's why we have the logic. If reader count equals 0, then do what? Release the lock of the database. Enough for readers, okay? Now, on the other hand, after that, of course, must release what? The lock on the readers, okay? And this is done anyway by all readers, mutex.release, because at the very beginning, they got hold on the what? The mutex itself to update what? The readers count. Now, the writer logic becomes much easier. For a writer to be active, then the writer only needs to get what? Hold on the database. So db.acquire. And its release is only db.release. As simple as that. Easy? Okay. Now, the last one is related to your homework, okay? You just get into it directly. Where is it? The dining philosophers. The dining philosophers, well, the problem already been explained before, right? You have a number of philosophers sitting around table eating sticky rice with chopsticks, okay, as you know. And the chopsticks are placed between philosophers. two adjacent philosophers, they are sharing a chopstick. So now these chopstick, they are the resources for philosophers to eat. Correct? Now, each one of these chopsticks is shared by how many resources? By how many philosophers? Two. For a philosopher, okay, the chopstick on the left is a resource that is either available or not available. And the chopstick to the right is also a resource that is either available or not available. So if I have 5 resources, if I have 5 philosophers, means I have 5 chopsticks, i.e. 5 resources. Okay? But the philosopher is only allowed to access a particular chopstick, okay? Which is either available or not available. So now we can say each chopstick is modeled by a binary semaphore. And how many binary semaphores we have? Equals to the number what? Of chopsticks. Okay, so we can create an array of binary semaphores. Array of binary semaphores. And the size of the array equals to the number of chopsticks, which is equal to the number of philosophers. Now, for a philosopher to eat, then it should acquire the chopstick to the left and the chopstick to the right. In any order, right? Right. So, if I have an array of semaphores and I call it chopstick, then for philosopher I to eat, it should obtain the semaphore chopstick, right? By saying what? Chopstick of I dot acquire, and then obtain what? The chopstick to the right, which is chopstick I plus 1, okay? So chopstick I plus 1 acquire, and you know the modulus there, why we have it, okay? Because we are numbering these semaphores 0 to 4 if they are 5, and then we have to iterate back, right? And then once these two chopsticks, the resources needed for the critical section are available, then we can start the critical section, which is basically eating, sleeping for a particular time. And then after that, releasing these semaphores. So you can call chopstick I release and chopstick I plus 1 release, and then start the non-critical section, which is the thinking. Right? Can we have a deadlock here? Is acquire what? Atomic or what? Or not atomic? Acquire. Acquire is one of the two operations on a semaphore, and it's atomic. Is what? Atomic. We assume it is an atomic operation. So we can't have context switch, or let's say, right, during the execution of this acquire. However, in between acquires, can we have a context switch? We can, right? So get this scenario. 5 philosophers eating, 5 philosophers are hungry. Means all of them will need to eat, right? All of them need to eat. So there will be acquiring. Let's assume that in the code of each one of the philosophers, we have a context switch after the first acquire. So the first philosopher acquires the chopstick to the left and got it, and then context switch. Then the next philosopher acquired the chopstick to the left and got it, okay? Then context switch and so. So what do we have? Each one of them holding one chopstick, and none of them is proceeding. None is proceeding, because every one of them will be waiting as a result of calling the second acquire, okay? Second acquire. So this is a deadlock situation, right? We can have other scenarios for this problem in which we put all the chopsticks in the middle. All of them in the middle. And if we do so, and we want to model now the chopsticks, then how can we model them? Excellent. One counting semaphore initialized to the number of chopsticks, right? Or the number of philosophers there. Excellent, right? And then we need, for the philosopher to eat, how many times should acquire? should call to acquire, right? Acquire, right? And basically, the acquire method should return, but we still can have what? Context switch between acquires and so. So that's basically what's related to your homework. You'll find the package where you need to complete a code in there related to these two scenarios, and then answer maybe two simple questions. Now, what you see is an implementation of a semaphore in Java, just a class that implements this semaphore. It's not handling lots of the other problems. In fact, Java supports concurrent programming. It supports synchronization, highly supports that. There is a package in Java, which is the java.util.concurrent package, okay? And it has many subclasses or packages, sub-packages in it. For example, the lock. We have seen different implementations of the lock, right? In fact, it has an implementation of the lock, and one of the classes is called reentrant lock. Reentrant lock. Do you remember the time also we implemented a locking mechanism using atomic instructions of the hardware? Right? We needed that. And we managed to do it using get and set. We managed to do it with swap as well, correct? Knowing that these are atomic. Java also supports such kind of atomic what? Variables. In fact, why we needed to do so in the very beginning? Do you remember the producer-consumer problem and the problem with count plus plus, count minus minus? Count plus plus involves 3 instructions. Okay? Imagine that count plus plus is 1 instruction. Do we need to do that kind of synchronization? So here Java supports you with an integer that is atomic. It has operations to operate on, and these operations are atomic operations. Okay? So I can define atomic integer, atomic boolean, okay? And call the operations for it to increment and decrement as well. Okay? So what we have, okay, are the following. We have reentrant lock, okay? This reentrant lock, basically you can just use it as a locking mechanism, create an object of, and then you can use lock and unlock. As easy as that, okay? You don't need to have the class of your own for the reentrant lock. As easy as that. Of course, we do that in try finally, because try to get the execution of the critical section, right? After obtaining the lock. But in both cases, regardless of whatever happening here in terms of exception or return, at the end we must make sure that we are releasing the lock after the critical section, right? Finally is executed in both cases. After normal or abnormal execution of the try. And in there we do what? Unlock. Similarly, we have the read-write lock. Read-write lock. So we have read lock and we have write lock, also supported by Java. Okay? We also have atomic boolean. We have atomic integer. And so with the operations of them, they have the operations compare and set, and these you can consider it as atomic operations. Okay? More than that, you can have atomic integer, atomic integer array, and atomic long array. And you can use them with atomic operations. Semaphore, that's the most important thing. We have Java supporting semaphore, a built-in class. Okay? A built-in class. And look at it. It has the method, so you can just create semaphore, but you have to import, okay, java.util.semaphore. Okay? And you create the semaphore. Binary or counting, it's up to you. It's how you use it, we said, okay? And you can call acquire release. Look at this. You can call acquire with number of instances of a resource. And you can call what? Release with number of instances. And these operations are what? Atomic. So now we don't have to worry context switch in between acquires or in between releases and so on. So please look at this, and hopefully that's going to be useful for you in solving problems related to synchronization. This is basically how you use it. Acquire, and the release should be inside the finally.